We're going to talk about trigonometric substitution. There's a mouthful. We use the trig identities as direct substitutions to then use a U substitution to solve your integral or evaluate your integral. Here, we're still going to use our trig identities, but it's going to be a little bit more hidden if you want to think of it that way. So the identities we're primarily going to use are going to be the Pythagorean identities. And make my O look like an O. There we go. All right. So there are three trig or Pythagorean identities. I'm going to write down the basic ones, and then we're going to use a little bit of an offshoot of these. So the first is sine squared, it's cosine squared equals 1. Reminder, make sure that you always have an angle with your trig functions. Sine in and of itself is meaningless. It's an operation. Sine has no value. Sine of x is something different. Kind of like square root is meaningless, but square root of x tells us something. Now, we're not going to use this one exactly. We are going to modify it. We are going to subtract the sine squared over. Also subtract the cosine over and do 1 minus cosine squared equals sine squared, but there's a little nuance in there that we prefer not to do. It's not wrong, and it's doable, and it's not that much different than using this form of it, but this way is just a slight little bit easier. We'll see why in a sec. Next one is, now if we would take this trig identity and we divide this one, and if we divide everything by cosine squared, sine squared over cosine squared would give us tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. And then we get this. So these three that are underlined are what we want. And now there's something unique here with the way they're set up, is that this one is a something squared plus 1, and this is a something squared minus 1. Now, this middle one could also be 1 plus something squared, so we take up both of those. But we have all four combinations of what can happen with a something squared and a 1, depending if they're both positive, if one's negative, and if they're both negative, it's just a different offshoot of them both being positive. So we want same signs and then different signs. And then depending on the setup that we have, it's then going to determine what we use. And we're going to have a U substitution of here we would make our U a sine. Here we make U a tangent. And here we make U a secant, or whatever it is that our variable is. So let's work through a couple of examples of these and see how we're going to use it. So first one up, let's do the integral of the square root of 9 minus x squared over x squared dx. So we have a something minus x squared. Since the x squared's being subtracted, we know right away that we want our x to equal something that has to do with sine. And we're going to have to use sine of theta, or whatever, some other variable. We cannot use x there because x is already used. But now we don't want our x squared. But in order for that to happen, we have to match those numbers in front. So if we would put a 3 in front, whenever it's squared, we get 9 minus 9 sine squared. We can factor out the 9 and we get our 1 minus sine squared. So we have to be careful with what number's out front. It's going to be the square root of that thing. Okay, so taking our derivative, we get 3 cosine of theta. So let's do some substitution now. So we have our integral, square root 9 minus divided by 3 sine of x all squared. And then our dx is 3, oops, there should be a d theta at the end of that, cosine of theta d theta. So remember, you always need a d something inside your integral. All right, so that looks like an utter complete mess. There is not much we can do here. And by the way, up here, we cannot split up and divide things because the whole thing's under a square root. So that's going to mess things up a bit. There are some ways we could handle this and approach it, but it's not going to make life any easier. All right, so let's go ahead and do some simplification. These should not be x's in here. Make sure when you draw your theta, it is a horizontal line across the middle of it. It's not a slanted line. That gives you a different figure, whether it's a 0 or a pi or something else. Oops, not cubed. That is squared. And then I'll bring my 3 out, and then we have our cosine over here. Square root. Let's go ahead and factor out a 9. So it's a square root of 9 times the square root of 1 minus sine squared. And we can separate. And now inside our square root here, we have that 1 minus sine squared. And this is our whole purpose of doing this trig substitution, is that 1 minus sine squared, we can change that into a cosine squared. And now square root of 9, we can make that a 3. Then it's a square root of a cosine squared all over 9 sine squared. Now we can multiply our 3 together and they'll cancel this 9. So those together will cancel that, simplify things a bit. All right, nice. Now this will give us a cosine. Technically, it's an absolute value of the cosine, but since we can just restrict our values for our theta to be between negative pi over 2 and pi over 2, then our cosine is positive, so we can ignore that. Now, if we multiply by that other one, we'll get a squared, and then we get sine squared d theta. All right, so how are we going to do this one? We can't do a u substitution because the top's a cosine squared. If we just cosine, would be nice. But using our other trig identities, our quotient identity, cosine divided by sine is a cotangent squared. And then we can change this. Squared minus 1. And now this is a very is the integral of cotangent. And that's an easy integral to do. So we have a, excuse me, not cotangent. This will be a negative cotangent minus theta plus c. Of course, we started with our x's, so we have to go back to our x's. So we have to do a little bit of work here. Now, back in the beginning, we said that x equaled sine, well, 3 sine of theta. Sine of theta equals x over 3. So here's our theta, but it doesn't matter where we put it. But sine is opposite over hypotenuse. If you do your Pythagorean theorem with these, this becomes 9 minus x squared. Should be plus or minus, but since we are limiting our values to over there, our x portion is going to be positive, or the horizontal portion, our adjacent is positive. So now, what is cotangent of this triangle? It is adjacent over adjacent over opposite. And now to actually get our theta, we would need to take this and do an arc sine plus RC. And let's make that 3 look. And so it's a little bit of a convoluted answer and looks kind of ugly, but the initial integral was kind of ugly to begin with, and it wasn't very friendly. So the important thing is that we are able to do this. And none of it's necessarily that hard. What do I have in here? Okay, this looks like one of our situations where we have to use our sine. So let's go ahead and do it. Work our way down with our simplification, and then go from there. Now, as I said before, that we could have used cosine here, but the problem with cosine is whenever we do the derivative, we would end up with a negative sign. And so it just introduces an extra negative into the whole situation. It's not wrong. It's doable. It's perfectly fine. But most people would like to keep this process as simple as possible. So we just avoid that extra negative. Keep it more optimistic. No negativity in your life. All right, let's try another one. And by the way, the reason we there is since we're going to take an arc sine of this, keeping in mind where your arc functions are defined. And so arc sine is defined between negative pi over 2 and pi over 2. And cosine is positive in those two quadrants. So a little more explanation of why we can drop absolute values and restrict our domain. Let's try another one. Let's do integral of 1 over x squared and then x squared plus 4. All right, right away, we have a plus sign in the bottom or inside with our x squared. It's x squared plus something. So that's x to equal something to do with tangent. And since we have a 4 there, let's make that a 2. So doing our derivative, we get 2 secant squared of theta d theta. So skipping a few steps in here, plugging in our 2 tangent for our x. Secant squared d theta. All right, we can factor out the 4 there, and then we would be left with a tangent plus 1. So I'll just move this to the top just to make life a little bit easier. And then we'll pull out 2 there, and we'll have the square root of tangent squared plus 1. Make sure your square roots in your division lines cover everything they're supposed to cover. Don't leave anything hanging out. And now this thing is exactly our secant squared. And then whenever we do a square root of that, we get our absolute value of secant. But again, if we would restrict our setup here to being where our and if we multiply that 4 times 2, one of those will cancel one of those. So we're left with a 1/4. We can pull that out front. And we have a secant over tangent squared. All right, so this looks kind of weird and unusual. How do we handle this? So one way to approach it is whenever you're given these different functions, change everything to sines and cosines. It's nice with tangents and secants because they have a relationship with both the Pythagorean identity and derivatives. But most people are more comfortable using sine and cosine, which also have a relationship with the Pythagorean identity and their derivatives. And it's a bit more straightforward, simple relationship with those derivatives. So cosecant, or excuse me, secant is 1 over cosine. And then tangent is sine over cosine, but it's flipped. So this is going to be a cosine squared over sine squared. Cosines can simplify. And we're left with this. Now this is a very nice U substitution. If we make our sine our U, cosine will be the du. So this is essentially u to the -2. So sine, and I don't want to use the -1 power. And now from here, we could also just rewrite it as a cosecant of theta. But of course, we do not want things to be in terms of theta. We want things to get back to x's. So remembering our initial setup, our x was equal to 2 tangent of theta. So there's our theta. Tangent is x in theorem. And we have cosecant. So cosecant is hypotenuse over opposite. And then if you want, you can just bring that 4 to the bottom. But we have our setup. Let's try another one. Your first thought might be, hey, look at that bottom. Let's make our x into a 2 tangent theta, just like we did before. But be careful. When we're doing these, don't get into a habit of just jumping to your first conclusion and getting in a rhythm with these problems. Always evaluate them from the beginning. And remember, if we make our u x squared plus 4, our du is 2x dx. So we just do a very straight u substitution here of making that a 1/2, 1 over square root of u du, or 1/2 integral u to the negative 1/2 du. Then add 1 and then divide by what that exponent is. So flipping it. And we end up with a square. Our u is x squared plus 4. Makes it look more like 4. All right, so be careful. Don't jump to conclusions of always just diving into what you're doing. Remember, check to see if U substitution works. All right, let's go with this one. Let's have dx over square root of x squared minus a squared. And they add a disclaimer of a is going to be a positive number. All right, so this one's a little bit more general. So it's something squared minus r, or so, yeah, our x squared minus a number. So we know that we want our x to equal a secant. Oh, not squared, just secant. So then we do our derivative. Theta in there. All right, so doing our substitution. Put in stuff for our dx. And then our bottom, it's going to be an a squared secant squared minus a squared. All right. Factor out your a, and that bottom becomes a secant squared minus 1, which becomes a tangent squared. Square root it. So we get our technically an absolute value of our tangent. But if we are restricting our secant, and they restrict it a little bit just between 0 and pi over 2, just to keep our tangent positive, we can then ignore that. A's cancel, those cancel. And we're left with just the integral of a secant. All right, we've seen how to do this one. By a secant plus tangent. Run together. So we're multiplying by 1, so we're not changing anything. And we end up with a secant. All over a secant plus tangent. And now, nice use substitution. The derivative of this is right here. And here. So addition being commutative, we can rearrange the order, and we're left with the natural log of a secant plus tangent plus c. There's the c. All right, but we don't want to have our answer in thetas. We want x's. So our secant, or excuse me, our x was a times secant. Adjacent. Use Pythagorean theorem to find your third side. And so whenever we do this, it's going to be the natural log of x divided by a plus square root of x squared minus a squared, all divided by a plus c. And then if you really wanted to, you can combine these together to give you an x plus square root of x squared minus a squared all over a. And then using your dividing logs, we can split that into subtraction. Now, we don't need the absolute values on this because we said before that a was a positive number, specifically because we knew we were going to get this later. And now natural log of A is just a number. C is just a number. We can just combine those into a new constant. And now there are some other ways to approach that if you want to. Let's get through a few you might come across. So let's go with the integral of, and let's do definite integral to show how this is going to work. And let's have this go from 0 up to the cube root of by 2. Or no, this is 3 square root of 3 over 2. Writing kind of small, it's running together a bit. All right, but we want to do the integral of x cubed over 4x squared plus 9, all raised to the 3/2 power. All right, so this looks like a mess. The top is an x cubed, so basic u substitution is not going to work. On the bottom, we are adding things, so therefore we want our x to be something with a tangent. In order for this to work out nicely, excuse me, let's flip that around. 3/2. If we are going to need to change our bounds as well. So whenever x equals 0, theta is also going to equal 0. But now whenever x equals 3 square root of 3 over 2, we get this. Now our 3's will cancel, our 2's will cancel. So where is tangent equal to square root of 3 or square root of 3 over 1? That is where we have pi over 3, 60 degrees. So make sure you change your bounds whenever you make your change with your variables. And now our x is going to be 3/2 tangent. So this will be a 27 over 8 tangent cubed on top. And make sure you change all your variables at the same time. Don't mix your x's and thetas. We want to get it all changed. Oops, that's just the top. I'm going to rewrite this because I'm going to need, oh, we can probably fit it in. Then our dx is 3/2 secant squared. And that is a mess. So 0 to pi over 3, 27 over 8, tangent cubed. Then times 3/2 secant squared d theta. And now for our bottom. When we square this, we're going to get 9 over 4 tangent squared. So that 4 will cancel the 4 in the denominator. Left with this raised to the 3/2 power. All right, so there's a whole lot going on here. So a little bit easier to do a square root of 9, which is 3, then cube it, so 27. So up here, the 27 and the 3 get multiplied, so that's 81. The 8 and the 2 get multiplied, that's going to be a 16. On the bottom, we'll divide by a 27. And then we have our tangent squared. Excuse me, that should be a tangent cubed. A secant squared. A d theta. And then on the bottom, it's a tangent squared plus 1, which gives us a secant squared. But that's raised to the 3/2 power. This can simplify with that one. A 3 tangent cubed secant squared over, that'll be a secant cubed. And we'll bring that 16 down there. And now we can pull this out front. Excuse me, our secants can simplify a bit. And again, that should be a secant, an absolute value of the secant on the bottom. But if we restrict our thetas to being first and fourth quadrant, we can. So now we have a bit of an issue with changing this and doing our assuming our integral. But again, like we did before, let's change everything to sines and cosines. So tangent is sine over cosine. So we have a sine squared, excuse me, sine cubed over cosine cubed. Then it's divided by a secant, which is the same as putting a cosine on top. So canceling out some of our cosines. We get down to here. All right, we can't use substitution for this. We're not multiplying, so we can't use some of the tricks we did before, but we can make a little bit of a change. That let's split this sine cubed into a sine squared times a sine. And then sine squared is 1 minus cosine squared. And then we'll multiply that sine that's remaining out front. Now this part in the middle, that fraction, can be simplified. And so we can split up that fraction to a 1 over cosine squared. And let's just leave it as 1 over cosine squared. Minus 1 times sine. And now this is a very straightforward U substitution that can be evaluated. Make your U a cosine, or if you want to, distribute that sine All right, so the second part is a very simple integral to do. This one, make your U a cosine. There's your du, sort of. You have to do a sign change there, but it's essentially a negative 1 over u squared du, or a u to the negative second. So we get 3 over 16. Then it's going to be a negative 1 over negative out front. Negative will cancel. That's just a positive. Plus cosine going from 0 up to pi over 3. So now plugging things in, so we have 1 over 1/2. And so 1 plus 1 is 2. We have a 2 minus 2. They cancel. So it's a 3 over 16 times a half. Our answer is 3 over 32. So now these problems, whenever it's a definite integral, they can be a little more complicated and you have to do the change of your values. But the really nice thing about these is you don't need to change back into your x's at the end. So that can be a little bit of a time saver. One more example, just because it's a bit. So for this one, if we try to do a U substitution, it's not going to work out quite so well on top. There are some things you could do with adding or subtracting different things in and then trying to split it up, but still that's not going to help us too much because we're going to still get back to a situation we have to handle. So let's take this bottom and let's rewrite it. Let's factor out the negative. Then we'll complete the square. And I'm going to put a minus 3. I'm going to leave it. But now completing the square. We want to focus on this thing, divide by 2, and then square it. But we added 1. We also, so this thing, we're adding 0. We're not changing anything. But let's now group these together. Oops, that is x plus 1 squared minus 4. And now if we distribute this, let's distribute that negative back in, 4 minus x plus 1 squared. So a little bit of a roundabout way of getting here. But now if we do a u substitution, where u equals x plus 1, du just equals, but we can manipulate this problem to give us u minus 1 equals x. So now our integral becomes a u minus 1 over square root 4 minus u squared du. Now this bottom our u substitution still is not going to work. And we could try and split it up to do a u substitution, but then we still have some issues with there. So our best bet is to just go straight for our u equals 2 sine of theta. So our du is 2 cosine of theta d theta. And then our multiplied by 2 cosine. And then our bottom, factor out the 4 under the square root. That's a 1 minus sine squared. Do the square root. Comes an absolute value of a cosine, but again, we're going to restrict it to the first and fourth quadrant, so we don't have to worry about the absolute value. Now this thing cancels with that thing, and we have a very nice integral to evaluate. So now integral here is just going to be a negative 2 cosine of theta minus theta plus c. But then our u was equal to 2 sine of theta. So drawing things out, there's our theta opposite over hypotenuse. And so let's do a change of a negative 2 adjacent over hypotenuse minus an arc sine of u over 2 plus c. And those twos are going to cancel. But again, we don't want our u's, we want our x's. So our u was x plus 1. So it's a negative square root 4 minus x plus 1 squared minus arc sine of x plus 1 over 2 plus c. So having a strong understanding of your trig properties, again, comes in handy, specifically your Pythagorean identities in this case. And then knowing how to translate between, knowing your basic definition of your trig functions to draw your triangles out and use your Pythagorean theorem to find remaining sides. All of that manipulation can be a little bit long and tedious, but it's not necessarily hard. Keeping in mind your three situations of whether it's a number minus an x squared minus a number, or an x squared plus a number, or a number plus x squared. Knowing what your substitutions are going to be with either the sine, the tangent, or the secant You can then change these from problems that are impossible to do with the way they're set up to problems that are fairly straightforward, if maybe algebraically heavy and trig heavy, but they're doable. And that's our whole thing, is we want to take problems and situations that seem impossible to do, and then we want to change the way they're written so that it's something we can manage. So Walt Disney had a quote of saying that it's kind of fun to do the impossible. When we're presented with our integrals in certain ways, they are impossible. So whenever we do the change, it makes them then possible. So we're in a sense doing the impossible, which is kind of fun.